This started like in 2003, when I went to a conference on space elevators and I was presenting an asymmetric capacitor thruster. And when I got back, my future advisor got very excited about space elevators. And he dreamt up this rotating version and a very large, unrealistic version, because if you look at it, it is. So what happens if you're looking down from the pole? The whole system is going around, of course. You know, you can see the Earth turning and the elevator turning, all that, but the elevator itself is coming out of the page and back in. So there's two perpendicular rotations, one from the Earth's rotation and the other one from the elevator. So it's a little bit like high lie. So, but I need to kind of, and then I got a little bit of money for doing this, and that was nice, and I just acknowledge that there. So I did my dissertation on that, and actually, I just want to mention here that in the thanks, there was some thanks for the computing, and that's what's been a struggle. It's really hard to run an entire programming and computational program on your own of this level. And I've been thrown off clusters, and I have old machines, and I pretty much just throw our hands up. So I got the idea of maybe just thinking about, how the thing would move. So that was cool, but I didn't make a whole lot of progress. So I just want to give you more of a background in hopes that you will want to collaborate with me. So it says here I teach math as an adjunct at a local university. So I'm back in the game a little bit. But the first part of this is this fiction to science, or scientific fiction. And this is a new idea of rotating space elevators. And he said, my advisor said, celestial scale spinning strings. And we actually had more success with smaller ones, and we'll get to that soon. This is an interesting picture of the Tower of Babel. And what they don't tell you is what you have to do above the clouds. And of course, that's why you have to go beyond geostationary. So this is obviously very fictional in its write-up, but it's pretty cool. Jack and the Beanstalk's got the same problem. It's a fantastic vision, but the space elevator is a fantastic vision, but it's also attainable, and it makes sense according to the laws of physics. We have skyscrapers and the Beanstalk. I couldn't believe that he let me put this in the thesis. So it's kind of fun. And then these are pictures you're very aware of, with the geostationary and the climate and counterweight. One thing that's kind of interesting is that if the counterweight is moving at sufficient speed, there will be no trouble with this system going around forever. But if it starts to oscillate, then you could run into problems. And we actually addressed that. This is just a nice picture. You all know this. This is a shot of Bradley Edwards, who I worked with for a while in West Virginia. This is just some papers. So this is a description. You can see the picture again with the rotation going out of the page and the entire system going around, from the sun perspective, inside the page. But the main thing is that you don't have to have internal engines or propulsion to transport far away from the Earth's surface. Now there is friction, but the concept, at least, we want to take this concept as far as possible, that you don't have to beam power. Obviously, you do have to beam power, but theoretically you don't, right? That's interesting. This is some of the math. These are the speed, or the omega of the rotating space elevator. The RSE is much larger than the rotation of the Earth, and that's significant. It's like 17 times or something like that. It's a lot. It's all Newtonian. I would like to do modal analysis. I have not, but I'd like to. The climate modeling dynamics, we cover that. And we talk about applications to launching spaceships. This is a lot of math, more math. Okay, so what we have is now this goes back to Buzz, his talk about the wind and about the interaction of the climber and the elevator in the presence of wind, right? So what happens is you can imagine that the wind would let you get a lot of acceleration on the climber, and if you could just get that whole thing to go up, you would get amazing speed. Okay, something like that. Um, and I'm thinking like it's a string-driven off resonance. It would be nice to have videos, but I don't have them. But in our simplified system, you can see that the distance from the Earth, just along the linear space elevator that you would have together with in the middle as an axis, that this thing's a very smooth oscillation. The climber just goes up and down all the time. And then this is a magical mass distribution. I spent a lot of time fretting about the fact that this was called magical. And it turns out that Blez again, so I know Blez. I'm just he actually has some equations for the same thing. So I'm kind of laughing a little bit about that. But it is a kind of a cool marching algorithm to get the tensions and the masses. And for the large elliptical elevator, this is all unrealistic, but we'll have a solution coming momentarily for this. This is just a picture of the sliding climber analysis of the energy. Same picture for the up and down. The idea is you want to go up to about halfway up and then take off with some other means of propulsion to get to the stars. This is what I've been thinking about a lot about highlight and about that you can put the ball in the middle there. And I was watching some videos, very hard to get this, but you can see that the highlight players can use the stick itself as a way to slide particles where they want them before letting them go. Okay, likely to get extra distance from the center, so to get speeds much higher than a baseball. We did some things about climbing threshold. It'd be also interesting to go back to Blez's discussion about how the climber is not taking off because the elevator is flat. It's sort of the same thing as if you don't have a fast enough elevator, you're just not going to get going. So that was sort of an interesting thought there. This is the new one. This is the uniform stress elevator. And it's kind of attached to a linear space elevator, okay? So this is about 200 kilometers. It's a much smaller object. It's 0.04 Earth radii. So I don't know what that is. It's a lot of kilometers, maybe 300. But this one here, it's not going to break necessarily. It's going to get things up to high speed. The problem is, how do you keep the top stable? You have to put it on a linear space elevator, or you have to have some other way of dealing with it. And the way right now we're dealing with it is on the right, spin launch. The gentleman, I forget his name, but he talked about spin launch, and he just meant to launch by spin. But that is going back to the HARP experiment where they put two things together and they shot things into space. This is sort of the same idea. You just get on, you start spinning, and you go into space. And with reference to the previous talk, no, humans don't go on this. Okay. So, but this is, that little, you see the thing sticking out, that's its propulsion into space. Kind of scary, right? This is some analysis that we did about launching, and we felt that of 4.22 minutes for this. This is like 200 kilometers wide or 150 kilometers wide, and it's going around once every 4 minutes. It's flying. But you needed something like 4 to 8 minutes to get them to launch. And if you didn't, obviously you couldn't launch anything. But I think the 2.11 minutes is unrealistic. But if you go back to here, you're talking this I call it as a compact space elevator. It's like a slingshot to the sky, roughly a space elevator. So from spin launch, very excited about their technology. They ignore my emails. But anyway, this is just some stuff. Oh, these are backup slides. What's my time?
You have 5 minutes.
Wow. All right, well, good. Thank you. So what happened was when we had the elliptical one, although it's not really as good of a thruster or a slingshot as the uniform space one, if you thought about the elevator consisting of the top and the bottom, and you stuck a massless stick between them, you came out with this idea that if the geostationary, well, if you went too far beyond geostationary with the top, you ended up getting unstable oscillations. And I made pictures of all different things. There was going around stable, there was hopping, which is hard to describe. And then, sorry about that, there was, I don't know if I have them. They had, this further down. But they had hopping and they had like total detach. The problem with detaching is that it's still going in an orbit, okay? It's just relative, we're turning, we don't know that the object is orbital, we just know we lost it. So we also had some collapse if we were running this thing too slowly. It would basically, I think, start developing all sorts of modes and then get period 3 and then just go crazy and lose everything. But this was a significant result that got published. A lot of work, a lot of work. These are the tension dynamics. You see, they're very stochastic. What a big mess. But for 10.83 minutes for the turn, and this is for the elliptical one, the big one, that the tensions were constrained and they grew for the other case. So we did this test of two things. And all I can say is never get your PhD in something if you don't love the topic. This is not worth it. And then we had quasi-periodic. They said it was okay, and then chaotic. So I had to have period 3 and or a massive amount of period doubling or something. These are some pictures that came along with it, and just to show you the quasi-periodicity, everything was kind of this is like you pick a point on the elevator and you analyze it, and you can see it's basically contained, and then the one on the bottom is not. And my advisor and I, we talked about random walk, so that was kind of fun. And so far, I should just summarize this now and let it be. So the rotating space elevator is a rapid space transportation system. It requires no internal engine. So then again, that's in the absence of friction. Obviously, these are huge distances, so I know that's not realistic. There are some nonlinear dynamics, but one thing that happened was I got some results that were so clean that my advisors said I was cheating. And I said, I couldn't even make this stuff up. I had no idea. And I think what happened was the mesh. I made the mesh so good that it just didn't have the energy to deviate from the system. Didn't have the energy to deviate much from the equilibrium position. So one of the things I would do is put more crazy conditions into the system. So that's what I would do. And I'm just going to try to get to some pictures here real quick that you might find interesting, and then I'll stop. I know they're there. There. Oh, no, that's not the one. That one. Those are the orbital ones. So that's all I got.
Thank you.
So
Really
work with me.
interesting.
Yeah, please work with me.
Jim.
Yes, from what I gather from your discussion here is that if you can imagine a cowboy with a lasso and the loop is in a vertical orientation and it's going east and west, that's essentially the structure of the rotating elevator. Am I correct?
Well, I think you're right that the Earth is, well, the problem is you have to be at the equator. So,
Right,
because you
right.
have to be, the rotations are at right angles. It's not, I think the purpose for the right angle was to get the climbers to go up. It's like a corkscrew.
Well, what I meant is that the base or the portion of the elevator that's in proximity of Earth is actually within the atmosphere, and
Unfortunately.
you're powering the rotation by a plant on the surface of the Earth.
Yeah,
Electromagnetic rail or type of deal
sure,
seems to
sure.
be what you'd be doing.
Yeah.
But then how do you attach your payload onto this fast moving tether? Does it kind of apply brakes to it until it gets up to speed, or what?
Well, unfortunately, we started at full speed, so we never dealt with the issue of what would happen if you had to get it up to speed. But yeah, some kind of rail, some kind of thing that would get that thing. It'd be like a corkscrew, but that you have some point you have to have the thing, attached in one spot of the earth with very little motion, and the thing in a, so it's like what is that? You said the lasso or something. You have
Right,
to be
right,
you have to be able to control it to get it into that motion, right? And
right.
so you're sitting there, and actually you're up your head, and I think the belt is actually going over your head, so it's going over your head, right? Like this.
Well,
I think
no,
it's just going westward.
no, it's going, it, the axis is horizontal. It's not over your
Well,
head. The axis is horizontal, like
well,
you're
no,
going to rope a calf or whatever like that. And,
well, I
and
mean,
so that means that the loop is in constant motion. Otherwise it collapses.
well, hold on a second. The spin launch is trying to avoid annihilating the cities, so the spin launch has that angle. We're actually, you're actually, if you're at the bottom of this thing, you look up, and it's going, and you just look at, your head just goes around, 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 watching that thing go around. But you don't have to accept our image. You can do whatever image you want, because the code will work,
Well, I,
however you
I
want to do it.
I meant to keep your not spin launch, but your design where you have a loop. Uh,
Yeah,
in order to keep it from collapsing, you're going to have to keep it in constant rotation.
that's true.
And
Yes.
and so that's like the lasso in a vertical orientation as opposed to a horizontal orientation.
Mhm.
And
Yeah.
and since
Oh,
it's
I
in
see.
motion, if you want to put your payload onto the tether, you're going to have to somehow you match the speeds with the payload to the rotational velocity of the tether.
I
So
think my
I'm not
email.
saying it's not possible. I'm just saying, how do you
Yeah.
envision doing that?
Well, that'd be great. I'd love to understand over email, but I think I've got Bluz wants to ask a question. I want to make sure I don't.
Yeah, go right ahead.
Good. Yeah, I was going to ask about deployment, but it sounded like that's something you haven't looked at too much. And so my
Yeah,
other
that's
question
fair.
would be about how much drag you have in the atmosphere, and if you've thought of any tricks to deal with that.
Yeah, I mean, I'm more interested in if you can use a spin launch system to get something into low Earth orbit, and then you start building an elevator from there. It's more of a sky hook, right? I mean,
Mhm.
I don't see this. I don't see anybody ever wanting to go on a string. Okay, I mean, if you've got spin launch and you have these things being thrown out there, and you got linear space elevators that get people safely up there, I don't know. No one would want to have these things rotating at that level and throwing stuff. You know what I'm saying? But it's a good way to get at other questions.
Larry.
What did you mean about a sliding climber? I got to admit, there's a whole bunch about this. I don't understand it all.
Well, if you
But
look at the science fiction author, I forget his name, but you saw a sliding climber there. I mean, obviously it was holding on, but it looks like it's sliding, right? It would have to be no friction. I mean, it could be magnetic levitation or something. But again, as I mentioned, the realism is that the thing's going to need extra boost.
why doesn't the shape become a circle?
Oh, well, you mean as you have climbers go up?
No, all your pictures show ellipses.
Well, there was a lips, and then there was a Hershey kiss. Did you see the Hershey kiss? Should I go
Yeah,
back to the Hershey kiss?
but I don't
Okay.
understand if the thing is rotating around like the lasso, why doesn't it become a circle?
Well, it would tend to do so under pressure from climbers. Is that if that's what you mean? I mean, you're right. It's a good question. There it is. You see the Hershey teardrop on the left?
Yeah.
So I'm thinking more about sky hooks right now. I mean, I don't think anybody's going to go and head to the Equatorial Guinea or whatever, not Guinea, Ecuador, and put one of these things in there. And it's just, it's going to annihilate boats and just, practically speaking. But I
Larry?
think that the you spin, but the spin launch is going to only take you to part way to the next level, and then it needs to have additional propellant, and you might want to have skyhooks up there that grabbing these and then turning and flinging them further so that they can before they even turn on their engines. I'm just spitballing here. That's why I'm here to ask questions.
Okay, well,
Larry,
this looks really quite a novel approach, especially the climbing the way it's done.